So, hello everybody. After covering flash distillation, rectification or rather fractionation, today we are going to discuss batch distillation operations. Now, normally what we find is we feel that batch distillation it is very simple and therefore it should be easy, but rather it is just the other way around, which is particularly because it is an unsteady state operation. So, naturally in that case most of the equations they will be written in terms of differential terms and that adds to the complexity of the design. But anyhow, batch distillation it is for operation it is not a very complex operation, I should say. In this case what do we have? Initially, just as we had mentioned in the introduction, there is a still. In that particular still it is charged with a fixed amount of a feed, right. So, therefore, here some amount of feed is there and say the total amount of the feed in say moles it is F and the composition is XF. Since it is a liquid feed, we take the composition as XF. This feed it is heated by a heating medium. In this case, what is the heating medium? It is the steam. The steam heats it, the condensate of the steam is collected and as it gets heated, then gradually the feed it reaches its bubble point. Once it reaches its bubble point, vapors start generating. What happens to this vapors? This vapor it starts rising, it rises through the vapor overhead line. This was mentioned in the introduction part as well. They rise up in the vapor overhead line. From there they come to the condenser. In the condenser cooling occurs, the vapors get condensed in the condenser, then they come and they are collected in the accumulator. It is usually termed as the accumulator. In the accumulator they get collected and after that the distillate is drawn from here. The distillate amount say over a particular time duration it is d, its composition is given by x d and distillation keeps on proceeding in this particular way. Now, as distillation proceeds, what do you expect is going to happen? Gradually, initially what will happen? The more volatile components they will start vaporizing and they will be moving, and with time gradually the more volatile components they get depleted in the feed. The feed becomes richer in the less volatile component. So, naturally with time what happens? The distillate also becomes richer in the less volatile component, or what I mean to say is that the distillate composition along with the feed composition it keeps on varying with time. We continue the distillation till we get the product specification that has been specified. Say suppose a product has been specified that we would like to have some particular distillate composition which I am denoting as XD average. We have to see that initially the vapor that we get that is richer in composition as compared to XT average. Then gradually the composition is going to be depleted in the more volatile component. One thing repeatedly I had mentioned earlier, it was there that naturally when we denote these compositions, they denote the composition of the more volatile component in case of binary mixtures or in case of ternary mixtures as well. There can be instances when the composition of the desired component is denoted by Xs, but mostly it is the more volatile component, at least for this particular class. So, therefore, initially we will start with Xd greater than Xd average, then gradually as distillation proceeds Xd will be depleted, it will become less and less till maybe it will fall below Xd average. We continue distillation till the average product composition meets our specification. Moment it has met, we stop the distillation process. Now, this distillation it was not very much practiced in chemical industries in earlier times, particularly in the oil industries etc., where normally there was a large scale operation with a huge amount of feed and the need for continuous operation was very important, but gradually the need is increasing, particularly with the importance of low capacity plants at the moment now, especially in the production of, I should say, pharmaceuticals, high specialty chemicals and food industries, etc. So, therefore, now more and more batch distillation operations are being performed in industries. Now, there are certain things that you have to remember, that a batch distillation will be opted only for low capacity plants, otherwise it becomes uneconomical. Now, there are certain particular situations where batch distillation is preferred. For example, suppose you get feed from different sources, or maybe you get feed from the same source, but the composition of the feed keeps on varying. Now, if this has to be accommodated in a fractionator, then in that case naturally the design has to be very flexible, and there is no guarantee that for all the feed conditions you get the product composition that you desire. So, therefore, for such a case, and when the amount is small, definitely you would prefer the batch distillation. It is mainly preferred due to its flexibility of operation. There is the other thing also, maybe in the same batch you can use it for different products. You may have different clients who would want different specifications of the product. It can happen the same client at different instances, due to the different applications they would want the different specifications of the product. So, for that particular situations, definitely a batch distillation is going to be preferred. You can monitor the product composition, and accordingly you can provide the product specification that is desired. Particularly it is important when the product purity is a major concern, and when off specification products are extremely undesirable. So, you can see that, well, we have reached XD average, and therefore, after that we will not proceed with the distillation. But normally for when the product purity is a major concern, then we would like to operate with a constant distillate composition, that is usually done in multi-stage batch distillation systems, where, as I had mentioned in the introduction and we will also be discussing at the end of the class, just above the still we have a column, and the column is operated in such a way that we get a constant distillate output. For this, what we need to do, we need to vary the reflux ratio. So, therefore, when the product purity is a major concern, we would like to opt for batch distillation. So, just summarizing the advantages of a batch process vis-a-vis a continuous process, we know definitely, see, the first thing, it's very simple in operation. There are not much control parameters. Definitely in a small scale it is cheaper, but this does not apply when the equipment, when we go for a larger scale, because we have to remember that the size of the equipment is larger compared to the size in case of a continuous operation for the same particular capacity. Why? Because the entire feed has to be fed in the still itself, and then the operation has to start. So, for a smaller scale it is definitely cheaper, but this does not apply when we go for a moderate or high capacity plant. Flexibility in operation we have already discussed quite naturally, because you can use the same still for different variations, or rather for different compositions of the feed. You can also use this for different compositions when different product specifications are required, and from the same equipment you can get different products. For example, in this particular case, if you see, then we find that maybe initially you get some particular product, say suppose which has a composition of say XD1. So, we start with some particular XD, we proceed till some particular XD2, such that the average composition gives you XD1. So, we have one particular accumulator where we keep on collecting till the average composition is XD1. Maybe you need another product which has a composition of say XD3. So, for that what we do? We have collected in one accumulator, we have collected product whose average composition is XD1. Then we direct the vapor to another accumulator. In that particular accumulator, maybe we start collecting from XD2 to XD4, such that the average composition is XD3. So, in this particular way, depending upon the number of products we can and the specifications, we can collect the products in different accumulators, and we can get different products from the same feed in the same operation. This is not possible in the single equipment in a continuous process. Now, even if it is simple, there has to be some particular controls for the quality control of the products and also for a safe and smooth operation. What are the things that we need to control? Just like all other operations, distillation operations, the temperature has to be controlled, the pressure has to be controlled, the level in the vessels have to be controlled. Where should you control the temperature? Definitely in the still, the temperature has to be controlled. This is one place where it has to be controlled based, and the pressure also has to be controlled at the top of the still. So, here we need to control the pressure. Based on this temperature pressure, the equilibrium data will be generated and we can start designing the batch column. The other place where it is necessary to control the temperature is the vapor which is entering the condenser. Here the temperature has to be controlled, and also it has to be controlled in the liquid which is collected in the accumulator. So, therefore, here also the temperature has to be controlled. Based on these two temperatures, you know very well that the temperature of the vapor which is entering the condenser, that is normally at the dew point, and the liquid which is leaving, it is at the bubble point. So, just like we have discussed in your fractionator, in this case also the condenser provides the latent heat for the vapor to be cooled from its dew point to its bubble point. And definitely once you know the accumulator temperature, if the accumulator temperature supposedly is going to be at the bubble point, you know that this feed it actually should be cooled before it is stored. So, what is the amount of cooling that is required, that also you can know from here. Levels have to be controlled, the level has to be controlled here, the level has to be controlled here. So, you need level gauge glasses in these two places. Now, normally if you have a very small plant, then all these controls they can be just at the column itself, and an operator can come and he can keep on measuring. If we have a larger plant, then there can be a telemetry arrangement along with alarms etc. associated to control and regulate the process parameters. Another very important thing has to be controlled here. See, the entire vapor which is generated, the entire distillation which is going on, that depends upon the heating which is being added to this particular still. So, therefore, the heating rate should be controlled, it should be as uniform as possible, because suddenly if a huge amount of heat is given and suddenly if there is a lot of vaporization, there is every chance that this vapor it will entrain some amount of liquid and take along with it, and that will reduce the efficiency of the distillation. It will result in poor fractionation. So, therefore, uniform heating is very much necessary, and the heating rate is necessary because that tells you the duration of the startup period and also the rate of distillation. How do we control this particular heat input? This can be heated either by an electrical heating. In that case, the power to the heating element can be regulated. We can use steam, just as we have shown here, we can use steam by heated stills. In that case, the pressure in the heating steam supply line, that can be controlled by means of a control valve. We may have circulating heating oils maybe from some other part of the plant. In that case, we control the flow, and in that way we regulate the heating. Well, when we go to discuss batch distillation, so along with the instrumentation, it is also very important that we understand the operation of a batch process. It is an unsteady state operation, naturally it has to go through time cycles. What do we have? We initially have a startup phase, and then we have a production run, and then definitely the ending phase. In the startup phase, naturally what you will do, you will be first inspecting the readiness of the equipment, and then you will load the feed in the batch still, and you will also start the coolant flow in the condenser. What does this do? This ensures that if you have some extremely volatile component, then you do not lose it. Whatever goes into the condenser right from the beginning is condensed and can be collected in the accumulator. So, we start the coolant flow rate in the condenser as well, And if suppose it is a vacuum operation, then the vacuum pulling also has to start from the very beginning itself, so that suddenly if the vacuum is started at some intermediate point, then it may lead to excessive vaporization. And after that, after we have started everything, we start heating the still. As long as the heating continues and vapor is being generated, but nothing is coming and collecting in the accumulator, it is the startup phase. We continue heating. During the heating, what happens? The vapor gets generated, and this particular vapor, it heats the upper part of the accessories, the pipings, etc., and then while it gets heated, some amount gets condensed, it comes back in the still, and then again it starts heating. So, in this particular way, the entire system gets heated, and after that, after sufficient amount of the entire vapor has gone, and then it gets condensed, and moment the first drop of the liquid it accumulates, it enters the accumulator vessel, we start the production run. In the production run, definitely we are producing what we want from the batch distillation process. So, during this production run, naturally the still gets heated and vapors are produced, the vapors are condensed, and then they come and then they are collected in the reflux drum. And if we require different products with more carts, each particular product that we are collecting, they are usually referred to as carts. So, if we need more than one cart, then naturally we will be collecting them in separate accumulators, and we will be controlling the cart specifications either by periodic sampling and analysis of the accumulator liquid. We can also ascertain the yield of the cart, and based on the previous information on the feed, we can decide upon the cart specification. We can also regulate, or we can also measure the temperature of the vapor which is leaving the still, because it is important to remember that this particular vapor temperature corresponds to the dew point temperature of the vapor at that particular instant of time. So, in this way we continue the production run as long as we are getting the distillate of our specifications, or possibly if the bottoms product is specified, we attain the specification of the bottom product. Depending upon the specification, we would like to continue the production run. When we find that our specifications are no longer being met, then we go to the end of phase or the cooling down phase, where the still is cooled and we prepare the equipment for the next batch. We cut off the heat supply line, and then there will be some amount of liquid which will be accumulated in the condenser. It is either mixed with the top product or it is mixed with the still. Well, so once we have understood the instrumentation and we have understood the cycles of operation of a batch, so definitely this is a design class. We would like to come to the design equations. And as I have already mentioned to you, the design equations, the main specialty is this is an unsteady state process. So, therefore, most of them they will be written in form of differential equations. Usually, what are the inputs, you tell me? The feed which is there, as I have told you, the feed is the input, the XF is the input, right? And as I have told you, either XD average will be specified, or maybe here XB, that will be specified, according to which we are going to perform the operations. Now, the famous Rayleigh equation is usually used for this. So, the Rayleigh equation is nothing, it is simply based on the overall and the component mass balance or the mole balance around the distillation unit. So, in this particular case, what do we have? At any particular instant of time, say the amount of liquid which is there, that is L moles, and the composition of the liquid in here, it is X in the still. Again, I will repeat, this X refers to the more volatile component. I will be deriving the Rayleigh's equation for a binary mixture. So, at the instant where the amount of liquid here is L moles and the composition is X, the vapor which is rising, that is V, and its composition is Y. Definitely this V, it condenses here, and that is collected as D. At the moment we are just discussing a single stage distillation unit. So, therefore, at any instant of time we find that the amount of distillate which is collected, that is equal to d, the differential of d. So, therefore, if from the from the basics, if I start, I know that moles in minus moles out is naturally equal to moles accumulated, the basic mass balance equation. In this particular case, you know, we do not have any moles in. So, therefore, moles accumulated will be equal to minus moles out. Tell me that if I do the total material balance, what is the moles out? dd amount at that particular instant of time. What is the moles accumulated? dl for that instant of time. If I do the component balance on the more volatile component, then in that case, in that instant of time, what is going to be collected? Minus y star of dd. This y star is in equilibrium with the liquid composition here, right. So, therefore, this will what will be the moles accumulated at that particular instant? It is naturally d of the amount which is there, which is nothing but sorry, L dx plus x dl. So, therefore, from here we know that y star dd, this is naturally equal to your L dx plus x dl. So, from there, from there we can very well define this as your dl by L, this is equals to dx by y star minus x, and this dl, it varies from what? It starts from the liquid, the feed, and it continues till the amount of moles of the bottom which is remaining. Correspondingly, this starts from xf and this continues till xb, isn't it? So, therefore, this gives you the famous Rayleigh's equation. From this particular Rayleigh's equation, if we integrate it and if we write it, then from this we get, this is ln b by f, this is equals to integral xf to xb dx by y star minus x. So, if we want to find out b, then in that case we need to integrate it. Even if we can find out d also from the overall material balance, quite naturally f equals to, for during the entire time interval, f equals to d plus b, we can find it out. But for finding this out, we need to perform this particular integration. And it is important to remember that naturally when we try to design any operation, we assume ideal cases. So, under ideal cases, this y star is in equilibrium with the x at that instant of time. So, therefore, now, this is the equation. So, now in order to perform this graphical integration, what you can do? We have already the equilibrium data with us. So, therefore, what we can do, for each particular equilibrium data, we can find out 1 by y star minus x. We plot it as a function of x. Maybe we have got some sort of a plot, and to perform the graphical integration, we need to perform it from xf to xb. So, we can find out the area under the curve, and from there we can find out b, provided f is given. We can also have an algebraic equation which can describe the equilibrium curve. We can use that algebraic equation here, y star expressed as a function of x. For ideal solutions, when alpha more or less remains constant, under that condition we know that y star can be related with x in terms of alpha, and therefore, for such situations we can relate y star and x by this particular equation. And once we can do this, then we can express b by f from this equation. We can do this. Now, this is applicable, as you know, this is applicable for ideal solutions, and particularly when alpha, it does not vary much during the process of distillation. What do you know? Initially, if xb is not known to you, then you calculate the alpha at the bubble point of the feed, and then you use that alpha. At the end of the distillation, you know what is your corresponding T bubble point for the bottom's temperature. Corresponding to that, you can find out P saturated of one component, P saturated of the second component. From these two, you can find out the alpha, which is nothing but equal to P saturated 1 by P saturated 2, where 1 is the more volatile component, and then you can compare the alpha at the end of the operations, say the alpha of the bottom with the alpha of the feed. If you find that they are not very different, there is no problem. If you find that they are quite different, then definitely you have to redesign the whole thing by taking a geometric mean of alpha for the feed and for the bottom temperatures. So, therefore, in this particular way it proceeds. Now, from the overall material balance, we also get what will be the average XD in this particular case. So, for the average XD, it simply we just do the overall material balance, which is FXF equals to D of XD average plus B of XB. So, from there we can find out XD average, and if you substitute here, if you substitute this as F minus B, and then generally this is the fraction of the feed which remains as the bottom's product. So, if you divide the entire expression, you substitute it with F minus B, and to divide the entire expression with F, finally the expression of XD average is obtained in this particular way. Now, normally, so therefore, these are the two equations that we use, and y star, it is calculated from this equation. To start with, initially what we do, we know XF. So, once we know XF, we find out YF star using this equation, where this X corresponds to XF. We find out this Y star. If we find that this Y star is greater than that which is specified for the distillate, we go for this particular process. If we find that Y star is less, we know there is no point in proceeding with this particular process. We will either have to reduce the pressure, or else we have to go for a multi-stage column. Just to give you a very concrete example, say we have started with a liquid which contains 75 mole percent benzene and say 25 mole percent orthoxylene, which means that your XF is equals to 0.75. Now, we need to design a suitable recovery process for the benzene, such that we would like to have XD average greater than 0.9. At all whether we can do it or not, for that we need to find out what is the Y star F, rather the Y star which is equilibrium with the feed composition. If you do it, the alpha for this particular case, we assume that the pressure of the feed, it is maintained constant at say 1 atmosphere, and in that particular case you can find out what will be the T bubble point of the feed for XF. How do you do it? You know the XF composition. So, therefore, you have to select the P benzene saturated and the P orthoxylene saturated in such a way that 0.75 P benzene saturated plus 0.25 P orthoxylene saturated, that will give you 1 atmosphere. So, accordingly, you have to select. Corresponding to this, you can find out the T bubble point of the feed. Now, this calls for a trial and error technique. So, whenever you will be given problems in assignments or in your assessment tests, definitely the bubble point of the feed will be specified for most of the cases. So therefore, we find out that that in this particular case it is around say 88.25 degree centigrade, and corresponding to this we find that the YF star it is around 0.9536, which is much greater than 0.9. So that this shows that we can proceed with this particular process. So what we do, we initially start with this particular value of alpha that we have found out from here. In this particular case, you can check it for yourself. Alpha is roughly around 7.45 or something. So therefore, and one more thing I had told you, that when alpha is greater than 3, we can go for a single stage. So therefore, this is greater than 3, we can confidently go for a single stage calculation. How do we go about the calculation? Initially, we assume some particular xb, which is less than xf. Corresponding to that particular xb, we calculate the still temperature. What is the still temperature? It is the bubble point temperature at P equals to 1 atmosphere, corresponding to xb, right. So therefore, we calculate it. Then using this particular equation, we calculate B by F from here. So therefore, we can calculate B by F. Once B by F is calculated, we can calculate XD average. Normally what we do, we tabulate the results. We assume different XBs. For each particular XB, we plot the B by F and we plot the XD average. We keep on continuing this till we get an XD average of 0.9. I have just done it and I have shown the curves here, which shows that more or less the XD which I have got, I have reached an XD average of 0.92 at a still temperature of about 104 degree centigrade, and under this condition the mole fraction in the still is about 0.4, and I find that the B by F in this particular case, it is almost equal to say 0.35 or something, which is not bad. Now, there is certain things that you have to remember in this particular case, that initially the still size that you are supposed to take, that depends upon the initial charge that you are supposed to fill, or the initial feed amount that you are supposed to fill there. And it is important for you to note that at the end of the operation, the amount of liquid that remains, that should be sufficient to submerge the heating elements. So therefore, if we have a very less amount of B by F in the still, then it will not be proper. Normally, what do we assume? We assume that the volume of the still, that will be equal to the charge volume plus some about say 30% extra to provide for the vapor space, and then very frequently we also have a demister pad. So these things have to be accounted for. If we have a foaming liquid, then this particular space has to be given extra, and at the end whatever volume you have, that volume of the bottoms should be sufficient such that the heating elements can be submerged there. Just I thought that I will repeat the process when the benzene with the same composition, maybe from some other source we have got the feed this time with the same composition of benzene, but this time it is contaminated not with orthoxylene but say with toluene. So, in this case, what can we perform this particular operation? So, in this particular case again we start with the same thing. We find that the P still in this particular case, it is 1 atmospheres, we have kept the same thing. Corresponding to this, the D bubble point of the feed, this is around 85.56 degrees centigrade, and for that the alpha that you get in this particular case, it is around 2.552, and so with this alpha we can proceed, and we find that in this case also for we going till xb equals to 0.4, we find that the maximum purity that we have got in this particular case, it is around 0.815. we are unable to use the single stage batch distillation still in order to recover 90% benzene when it is contaminated with toluene. So, therefore, this suggests that for this particular case we have to, and one more thing important, you will find that the B by F in this particular case, that is also around 0.15, which is bit low. So, therefore, this suggests that when benzene is contaminated with toluene, when the alphas are not very far off, rather it is not much higher than 3, in that particular case the single stage is not a very good option. For such cases, either we have to reduce the pressure, which is not always economical. For such situations, we have to go for the multi-stage column. One small thing I would like to mention, which I had forgotten to mention in this particular case, see, when I was doing this, initially I had assumed an alpha of 7.45. At the end, what I found was that for xb equals to 0.4, the T bubble point for the bottoms, that was equals to 105.1 degree centigrade, and therefore, the alpha at the end, if you calculate, you will find that is equal to 6.582, and as a result we had used the alpha average in this particular case, and we had done the entire calculations with an alpha of 6.9929, and the graphs have been generated from that particular alpha. For the case of toluene also, we had made the check, it was not extremely much, they were not extremely different. Initial alpha was say 2.552, the end alpha was 2.468. So, therefore, in this case also the curves had been generated with an alpha average, but if you can do it with the initial alpha also, it is not bad. But definitely under this condition, we find that we have to go for a multi-stage distillation column, where what we have a tower above the still, and in this tower either we have sieve trays with no downcomers, since we need very few number of trays. So, therefore, tray efficiency is not of a concern. So, we either use sieve tray with no downcomer, or we used packed columns in this particular case. So, the vapor which is generated, it rises up, it goes up, reaches the condenser, comes to the accumulator. From the accumulator, just like a fractionator, we withdraw some amount and we introduce it as the reflux, and the rest amount it is withdrawn as a distillate. This reflux, it comes in contact with the rising vapor, enriches the vapor further, and so therefore, this particular system it is similar to the fractionator with only the rectification section. So, naturally, we usually for small units, what do we find? For small units, the column, it is located just above the still, and for larger systems it is usually located by the side. But when it is located at the side, it is important that it is located at an appropriate elevation, such that when the liquid is falling down from here, it can enter the still by gravity flow. And for such a case, you can very well understand, since it is a rectification section, it is only just a rectification section of a fractionator. So, normally we use the McKeep-Thiele diagram for the rectification section in order to obtain the number of trays and the reflux ratio. And there is just one thing I would like to mention, that with the reflux, the column is operated under two conditions. One of them is that when the distillate product has to be, it is it is very important. For that particular case, we keep the distillate composition same, we vary the reflux ratio, and we control it by controlling the top temperature, because the top temperature is going to, if this is kept constant, then Xt is kept constant. So, this is kept constant by varying the reflux ratio, and we continue this particular operation till the point we find that the reflux ratio has reached an uneconomically high value. But the easier thing to do is when we can keep the reflux ratio constant. So, under that condition the XT keeps on varying, we keep the reflux ratio constant and we continue the operation till XT falls below a specified value. So, therefore, when we are going for multi-stage batch distillation, the operation can operate by two ways. It can be by keeping the constant distillate composition and varying R, or it can be by maintaining a constant reflux ratio where the distillate composition varies. This is easier to do and therefore, this is practiced only when there is a strict specification on the distillate composition, we go for this particular operation. So, I think this is this much for today. We have discussed a single stage batch distillation and we have also done a problem in order to just to show the application of Rayleigh's equation, and I have also touched upon the concepts of multi-stage distillation, batch distillation. Thank you very much.